sorry dat ik dit zo doe, maar ik moet ook snel weer weg om mensen te gaan begeleiden. Sorry.
Ja, precies.
Good afternoon, everybody. We are about to start with the meeting today, the symposium. If you'd like, please join us here on the stage, at the stage. Okay, good afternoon. Welcome here at the ELAT-NL test lab at the Symposium Testing of the Future of EV Charging. My name is Lonneke Driessen and I work here at ELAT-NL as the director of the test lab, so the location where you are now. I have a background in electrical engineering at the Technical University Delft, where I studied power electronics and electrical machines. And this was 30 years ago, and 30 years ago this topic was a little bit dusty. And all my friends moved on to computer science or telecommunications, which was very hip and happening 30 years ago. Everybody was migrating to mobile networks. But I chose power electronics and electrical machines. After my education, I joined a grid operator in the Netherlands, a Nexus. And little did I know that 30 years later, I would be standing here in a test lab where we test everything related to power electronics and electrical machines in vehicles. This is the ELAT-NL test lab. ELAT is a non-profit foundation founded 15 years ago by the Dutch grid operators. And as you know, all across the world, grid operators are responsible for providing a safe electric grid, reliable, affordable. In the case of the Netherlands, we are owned by the regional provinces and cities. It should be of good quality, so the electricity we provide should be of good quality. All those things are really important to grid operators. This is what we do. And 15 years ago, when the grid operators saw this new load coming onto the grid, electrification of transportation, they said this is something that's going to be important and we want to learn and we want to prepare for the future. So that's why they founded ELAT 50 years ago. ELAT does a lot of different things. We do data outlooks where we explore what industries will electrify, at what pace, where they would like to charge and with how much power, so we can prepare our grid where we place reinforcements. We do a lot of projects, smart charging projects, so changing the speed of charging to accommodate for the grid capacity. We do innovation pilots, we do lobbying, we do education, we do a lot of different things. But the reason why we're here today is because of all the testing that we do. because testing is a great way to meet industry players, to learn, and to improve together. So for this testing, we have now this new test lab, and today we have this great symposium prepared for you with several speakers. So first of all, we will have a presentation by Thijs van Wijk, who is the manager of the ELAT-NL Test Lab. And this will be followed by a presentation of Tim Slangen, who now works for grid operator Stedin, but who has done his PhD studies in power quality and still is active in the field of power quality. So he will present a bit more on that. Then we'll have a little time for questions and answers. Then we'll have a coffee break. After the coffee break, we will have a presentation by Beat Kreuter from DECRA, who is the expert in our industry when it comes to testing, standardization. And we're very happy that he will also be sharing his knowledge with you here today. Then we'll have a presentation by Erik de Jong of Kima Labs, and he will tell you all about high power charging, something that's coming to the market with all the trucks that are electrifying and heavier equipment that's also electrifying. Also followed by a short time for questions and answers, and then we'll have a presentation by Wolfgang Kalthoff from Keysight. If you want to test, you need test equipment, and Keysight is one of the main providers of testing equipment in e-mobility. So they will present what they do, and followed by a nice demonstration of the Keysight system that we use here in the ELAT Test Lab. And after the demonstration, we will wrap up with drinks, and we are here available for any additional questions that you may have. But before we start with the symposium, I'd like to give you a very brief safety speech. So if in case of an emergency, we have two emergency exits. One is to the back, to the large doors that will open. And the second way to exit the test lab is to the side entrance. The restrooms, if you want to wash your hands, are available through that door to the right. Please be careful when you walk around. Don't smoke. This is a non-smoking building, of course. And be careful with all the equipment that we have here on display. And if there are any questions, please ask me or any of my ELAT-NL colleagues. We will help you with what you need. So with no further ado, I'd like to invite to the stage Thijs for the first presentation.
Well, thank you, Lonneke. Okay. Let's see. Yeah, there it's going. Well, great to have you all over here. It's nice to see such a big crowd for such a specialized subject. As Lonneke just introduced myself, I'm Thijs van Wijk, the technical lead and the manager of the ELAT Test Lab. And I'm going to tell a thing or two about our future plans for the ELAT Test Lab. But first of all, who are we? What is the ELAT Test Lab? Well, we are proud to be the EU largest test site for the grid integration of electric vehicles and charging stations. We're non-profit organizations, also non-profit lab. The tests we do are pre-certification and pre-normative. So it's just advisory tests to help the manufacturers to develop further and to better integrate with the electricity grid. We do cooperate a lot with the more commercial test labs, like the DECRA, like the KEMA labs, and like DNV. We're also all here, well, at least the KEMA and the DECRA are also here to present. And they're also all located here in Arnhem. So that's a great way to cooperate and to do local cooperation too. And then apart from testing, we also do research. And the research part focuses on power quality, and especially related to the so-called superharmonic distortions. And for this we have, of course, our test lab, but we also do perform field measurements. And we're with about 10 employees. ELAT itself is bigger, about 50 FTEs. But at the ELAT Test Lab we are with 9 people and 1 intern at the moment. And well, this whole test lab has been made possible by funding from the first place the grid operators of the Netherlands, of course, but also by the Ministry of Infrastructure and Water Management and the province of Gelderland. So to go further, well, why do we test? That might be a question you might ask yourself, because, well, we're grid operators, so we're not a commercial certification lab or something, so why do we perform these kind of tests? Well, for us as grid operators, it's important to know for sure that the chargers and vehicles are able to do things like smart charging, because we are responsible in the essence for the delivering the power to the devices, and the capacity of the grid, that might in some cases be a limiting factor. So we want to make sure that if there's a lot of vehicles that want to charge, that we are able to, that these charging stations are able to be controlled, to be lowered for a certain moment in time, for instance, or actually be hired for a certain moment in time when there's a lot of renewable energy available, for instance. Just to make sure that we can cope with all these electric vehicle charging at the same time on the electricity grid. So that's why we perform tests on smart charging, but also on cybersecurity, because we also want to make sure that nobody will be able to hack the charging stations and hack the charging system in general, because if you can play around with that amount of power, you might really cause blackouts or any other issues in the electricity grid. Now, the second part why we test is the power quality, or the quality of the grid. Charging can have an influence on the voltage of the electricity grid by distortions that come from the charging station or the electric vehicle, just, well, where the AC/DC converter is located. And these distortions might influence the grid, the voltage of the grid. And the voltage of the grid also needs to be within certain limits. Because otherwise it might cause well, issues with the grid itself, with transformers or with the cables, but also with the connected devices to the electricity grid. And we as grid operators are responsible for this voltage quality. Then we test the emissions, but we also test the immunity of the devices themselves. That's also why we have this new testing equipment that will be demonstrated later, to also create distorted electricity grids to see if a charger or a vehicle is able to cope with a voltage that's not perfect, like not 230 volts, but 200 volts, and it also has some ripples on top of it. And another reason why we perform these tests is because a lot of these tests are not being performed at the moment because they're not in a standard or in a norm or in a sort of certification process yet. For instance, the superharmonic distortions, there are no emission limits for those yet. So we help to define these limits by doing research on these kind of distortions. And also because, like a vehicle, before a vehicle can enter the market, it needs to comply to all kind of different rules and certifications, but really things like power quality or the ability to do smart charging, that's not really in the type approval for an electric vehicle yet. And so we fill up that gap at the moment, but we're also in talks with the UN ECE, for instance, to get these things into the type approval for vehicles. So it will eventually be like a typical test that can be done by the different test houses. So we perform 6 types of tests at the test lab. Well, first of all, interoperability. That just means we have all these different chargers you see over here. We get a lot of electric vehicles over here. We connect them to each other, and we're just checking if they're able to communicate with each other during regular charging, but especially also during smart charging. Then there are the smart and bidirectional charging tests. Those are going a bit more deeper into different smart charging scenarios, and also bidirectional charging scenarios, where we just test the functionality and if the response is on time and if they always stay on the right level, so they don't overstretch the amount of current they are allowed at that moment, or that they respond in time or don't fall asleep after a longer pausing period. Then there are the power quality tests. So during the test we just measure and see if we measure any kind of distortions coming from the devices. And we create reports of them and we advise the manufacturers on their power quality behavior. And now we can also because of bidirectional charging, there's also the need to test the requirements for generators compliance, because as bidirectional charge, you're also feeding back energy to the grid. There's some more compliance needed to be able to be allowed to do that. So with our new testing equipment, we'll also be able to test this compliance. Well, the cybersecurity test, as just mentioned, we can do a check of the different chargers that come here. When a charger comes here, we do a small integration test where we connect it to our back office system, we connect it to our grid, and we do also a cybersecurity scan where we check if there are any open ports or any other weaknesses into the device that can be used for an attack or something. Then there's the arbitration test. That's especially interesting when there's an issue in the field with a certain type of charging station and a certain type of vehicle. We can be like the man in between where you can come test. We're a neutral party in this, and we can help to solve the issue. And finally, there's the grid connection test, or the grid operator test. And this is actually a test we do here in the corner of the lab, where we get every AC charger that needs to be installed in the public space in the Netherlands. It needs to comply to certain rules from the grid operator about the connection, about the size for installing the smart meter, for instance, and the working space there is for the technician. And that's also a check that's performed here in the ELA test lab. So those were the tests. Well, about our power quality research. Well, the upcoming research here is we're going to do some more field research on the impact of heavy-duty charging hubs on the electricity grid. So there are now different charging hubs created or being created for trucks, where there are multiple heavy-duty DC chargers, like 350 kilowatts and more. And what kind of impact will this have on the electricity grid? So we're going to perform some measurements over there. We're at the moment, we have an intern, Tigo, and he's researching the impact of the different DC chargers we have over here on the electricity grid, mostly regarding the superharmonic distortions coming from these devices. Then now we're also able to test bidirectional charging. We're also going to check how these kind of feeding back energy to the grid, what kind of influence that has on the power quality, and if there's a difference between this and charging, and also regarding the superharmonic distortions, if there's a difference in those two situations. And for a project that will start next year, we'll also be creating a setup where we want to test the immunity of devices to superharmonic distortions. So we want to inject these kind of high-frequency distortions to our electricity grid, to our testing grid, and see how vehicles respond to those. And finally, getting later this month, we're getting a device where we can measure the impedance of the grid on superharmonic distortions. And we also want to use that for more field tests in the different projects we're using, if we're into. And it's an important part for knowing what kind of impact superharmonics will have on the electricity grid, how the distortions will flow through the grid, and how immune devices might be. So there's a lot of research going on, at least a lot of research is going to be started. You know one intern, maybe you know some other people that might be interested in an internship here or in a PhD assignment or something, then we're all ears. So, and for now, this is a bit of our future focus. Let's see. Yeah, this is nice. So in 2024, in the past we did a lot of AC Mode 3 charging of electric vehicles. This year we're starting a project where we will test 150 passenger vehicles on their AC charging behavior with Mode 3 communication. And after that, we want to get rid of that type of testing, because there's already done a lot of testing on AC Mode 3 charging. We know what goes well, what goes wrong, So eventually after this project, we will share results, a best practices document, and we expect the market to pick that up and get iron out the last issues with AC mode recharging. Because, well, we want to invest or put more time into the newer developments, like bidirectional charging, of course, including these RFG grid code compliance, and maybe also the efficiency of bidirectional charging. So that might be an interesting thing too, to also get the business case regarding bidirectional charging well rounded up. Then at the moment, well, as you see, we have a lot of DC CCS heavy-duty charges over here. So we're putting some effort into testing those. But in a couple of years, well, there will be MCS charging, of course. So during the coming years, we will lay more focus on MCS. Maybe even upgrading our testing system, but let's see how that goes. Well, and so that's the testing part. And for the power quality research, there's a lot of overlap, of course, but we're going to during the testing of the DC charges, we're also going to measure the power quality of those, of course, the power quality influence. But in essence, that will also go more to the influence of MCS charging over time. And the interesting things are that we are going to start with these superharmonic emissions and superharmonic immunity testing in time. So how are we going to do that? Well, first of all, of course, we have a nice new device that will be demonstrated later this day by Robert and Wolfgang. And so that's a nice new setup. 360 kilowatts of power, so a lot of power under control, and we can create different test setups where we emulate an electric vehicle or a DC charging station or an AC charging station. And it's all hardware in the loop, so all the energy we're using, we take out of the grid, we can also put back into the grid, so we don't lose that power. Then we get a grid impedance tester. Like said, we want to investigate the impedance of the grid for high-frequency distortions. And this device, I should have this one, yeah. This device will is able to do that. You get these kind of graphs where you have the impedance per frequency in a spectrogram, so you can see, okay, how resistant actually is the grid for high-frequency distortions. You can also use this to test devices, so you also know, okay, how well do these different devices absorb these kind of distortions. So that helps you to understand where these types of distortions are going in the real grid. And that also helps to create knowledge about these types of distortions and to also eventually set limits. And for injecting the superharmonics, well, there's no system available yet. We just have a design outline. And well, this is something we want to build up somewhere in 2025. Still, well, a lot of research needs to be done to figure this out, how we are going to do this. Any input from the audience will be welcome. And I talked a lot about superharmonics now, and it might be a foreign subject to a lot of you guys. So now I want to give the microphone to the next speaker, Tim Slangen, who's actually Dr. Tim Slangen now, because, well, he did his PhD on superharmonics and the effects on the electricity grid.
You may hear a little bit of noise in the background. That's actually the cooling of our test system, so it is maybe a bit disturbing, but it's a working lab, as you can hear, so sorry about that.
Yes, it's working. Okay, well, thank you all for being here today. It's also great for me to be here today because it's a very familiar place for me. I'm now working at Steden, but I have worked here for more than 5 years, so I'm really happy to be here today and to see all the improvements that the lab has been made in the past few months. So my name is Tim Slangen. I'm currently working as a grid strategist at Steden, working on power quality and network protection with the Department of Asset Management. As I told, I did my PhD research on power quality at ELAT NL in cooperation with the Eindhoven University of Technology. And I learned a lot about power quality, the effects of new devices, of the energy transition on these phenomena. And I will tell a bit more about that today. Yeah, we saw it in the previous slide as well. If you're interested in reading my thesis, I've included the link in the presentation, and feel free to contact me with any questions you have about this. So a bit about Steden. Steden is a grid operator in the provinces of Zuid-Holland, Utrecht and Zeeland, and also some other small areas in the northern part of the Netherlands, just for the gas networks. Responsible for operation, maintaining and management of the electricity and gas networks. We contact about 2.3 million households to the network. The area we are controlling is a quite dense and complex area. We have 3 of the 4 largest cities of the Netherlands, Rotterdam, The Hague, Utrecht, and a very large industrial area around the port of Rotterdam. So it's an area with a lot of energy demand, a lot of complexity, and also a lot of challenges. Some numbers about the company, always interesting to show. So about 2.3 million households connected. Above that, a lot of industrial, very large customers. Last year we transported about 24,000 gigawatt hours of electricity, and the average interruption duration index is always very low in the Netherlands and also in the Steden network. For the whole year, the average interruption was about 20 minutes for the electricity grid and about 45 seconds for gas. So that brings the uptime of the network to 99.996% for electricity and 99.9999% for gas. So that's beyond the world's best standards that we have here in the Netherlands. Also explains why that many data centers want to be in our country, because the grid is so reliable. So in the Netherlands we have the 3 largest DSOs, Steden, Liander and Enexis, controlling the electricity network, everything below 150 kilovolt and 150 kilovolt, or 110 I should say, and above is controlled by TenneT, the TSO. At Steden we have divided our network in different voltage levels. It's a bit of a mess because we have a lot of voltage levels. That has some historical reasons, and also because of we merged from different grid operators into a larger company. That's why we have all the different levels at the moment. But primarily we use everything above 25 kilovolt for transport over large areas. That's what we call high voltage. Between 10 to 25 kV for medium voltage for distribution of energy, and then going down to 400 volts to the low voltage customers, all the way at the bottom. So my presentation, I divided it in 3 parts. I will first give a brief introduction on power quality. Might be a new topic for some of you, or might need some refreshment. Then I will talk about the new technologies that we see in the network nowadays, and also about the challenges that they bring with them. So power quality, that's a term that's often used, like, oh, we have good power quality, bad power quality, but actually a lot of phenomena covered into it. And this figure is not complete, so some are still missing, but it is about harmonics, imbalance, flicker, voltage level, all these kind of things, which is also regulated in a standardization framework for the grid operators, but also for manufacturers of equipment, to make sure that the electricity network is always working with all components that are connected to it, and vice versa, that the components are not disturbing the electricity network. Power quality is a lot about responsibilities. So this it's in fact threefold. You have the customers, the grid operator, and the manufacturers of devices. Well, the customers are all the way at the top. That's the best position to be in because you're not responsible for anything and you can complain about everything. So that's really the best position to be as customer. The grid operator is then responsible for what is offered to your connection, so mainly the voltage. And the device manufacturers are responsible for what they take from the network or inject into the network, because this affects the voltage as well. So there's a whole set of regulations talking about what the manufacturers can, or the device equipment should be compliant with, and for the grid operator to also ensure that our customers have a good voltage supply. It's also about compatibility, because the electricity network is a very large system. There are a lot of components connected to it, and this all should work together in a good way. So a figure that is often used is this one. It has multiple aspects. On the bottom left, let me see if this works. Yes. There's, for instance, the emission limits of individual devices. So this is a quite low limit, because in the end, this emission might result in a higher level for the whole system. Then the levels at which systems should be immune, or components should be immune, is always higher than the emission limit. So that's over here. And what is in between is what we call the compatibility level. And as you see, there's a bit of an overlap between the largest possible emission of a system and the lowest immunity of equipment. And this means in practice that indeed the worst 5% of equipment will not perform well in the worst 5% of the grids, but that's something we accept. Because in order to separate the curves completely, that would be economically unfeasible. That would cost a lot of money. So that's why we put the compatibility level at about an overlap of 5%, so that 95% of the equipment works well in 95% of the environments. That's where this level is set to. Now, power quality, the word power is of course a combination of voltage and current. And then if you take the ratio of voltage to current, you get impedance. So power quality is about voltage, current, and impedance. So, that's Ohm's law. That's not that fascinating, I would say. But it is very interesting to understand this basic concept. Because on the one hand, the network impedance and the voltage, that's where the grid operator is responsible for. And on this side is the manufacturers of equipment. They put load to the network that draws certain current. And in the end, this current, in combination with the impedance, will disturb the voltage. So power quality is always about voltage and current and the interaction between both. And this is really important because when measuring or monitoring power quality, it's often only about the voltage. And of course, that's the real impact on the network. But it's also important to look at the current as well, to understand why things are happening in such a way and to see the whole picture. We are, of course, in a transition. The energy transition is ongoing. And this means in order to reduce our overall energy consumption, we need to increase our electricity consumption. And it might sound a bit strange, but in order to make more use of renewable energy and more efficient use, one way to do that is to, for instance, heat your house not by gas, but by using a heat pump. So we need to use more electricity to reduce our total energy consumption. And one way to do that is to change the way we use energy in our network with new devices. And those new devices are often based on converters. So the traditional networks they work on an AC voltage, alternating current. Voltage, if you translate it, is a bit strange. That's also what the network offers to the customers. But most devices work actually on a DC voltage, so direct current voltage. This means that in order to use your electric vehicle or your heat pump or to connect your PV installation to the network, you need to convert this AC to a DC or vice versa. And in order to do this, you need a converter. And you can find the converters in all kind of devices that you have in your house nowadays. The charger for your phone, for your laptops, LED lights, but also the larger devices like we just talked about. The thing with these converters is that they make sure that we can use renewable energy, but they also put some challenges on the network. They can namely cause disturbances in voltage and current. Now, how does that work? I will explain. So ideally, the waveform of the network, voltage or current, is a sinusoidal waveform, like in the left part of the figure. But when a device is connected to it, it might inject an additional distortion component on top of this ideal waveform, which means that the resulting waveform will then look like in the right figure. Now, this is okay, as far as it is within the limits. But nowadays, with the increasing share of converters, we see these distortion levels also increasing in the network. In the past, distortions were mainly low frequency, so that's what we call harmonics. So that's an example in the top figure. These are disturbances with a frequency below 2 kilohertz that are at the fundamental multiple of the fundamental, so it's quite easy to measure and to look into it. It's also really well covered in standardization because that's been known for several decades, harmonics. So that issue is quite under control, I would say. But nowadays, with the increasing numbers of large converters who make use of switching frequencies above this harmonic range, because that's more efficient and cheap to build, there's also an increase in supraharmonic emission levels. Supraharmonics are at higher frequencies than the harmonics, so that's everything above 2 kilohertz. They are totally unrelated to the fundamental, so the name harmonic would imply it's a multiple of it. It is not. And the research is only there for about 10, 20 years, so it's a really new topic, and there are no limits on it yet. And this is where the main challenge lies at this moment with all these new converters in the network and the disturbances they bring. Now, this was also the topic of my PhD research, so I will dive a bit deeper into this phenomena. So the sources of supraharmonics, it's not that new because we know all these small devices already. Moved in the past years to larger electronic devices that you find in your house, so the PV inverters, the charger for your electric vehicle, heat pumps. But in the future, and not even future, also nowadays, is increasing to larger installations like the large fields with PV plants, the large fast charging stations. So these type of devices are growing not only in size, also in power, and by that also the disturbances will increase in the network. Now, here's a whole list of things supraharmonics can cause, interference and impact, but I always think a picture tells more than 1,000 words, so I will show some examples. Because of this lack in standardization, components or equipment are not really immune to supraharmonics. So things that can occur are, for instance, the failing of protection systems, heating of equipment, failure of it, audible noise from induction cooking plates, other equipment, failing of cable terminations, coffee machines that only make tea. So it's a whole bunch of quite specific problems that occur, mainly due to a lack of standardization. And a lack of standardization, there is something, this is a list, I will not go through it all the way, but the domain 2 to 150 kilohertz, there is something written down in standardization, but unfortunately the list of missing standards is at least as long. So these are issues that people are still working at, and where there is a need for standardization in order to solve these problems. So we talked about broadly power quality, the new technologies we see in the network, and a bit about the challenges. But I will now dive a bit further in the challenges that I found during my PhD research here at the ELAT Test Lab that are related to electric vehicle chargers, but also apply to all different kinds of larger inverters. It's again threefold. I will talk a bit about primary and secondary emission, about factors that influence emission of a device, and about impedance, and that is what Thijs also was talking about. I said it's right, impedance, it should be impedance, I think. Primary and secondary emission, this is a very important distinction that you should make if you are going to do research on a power system, on equipment. Because if you're just going to measure a device that's connected in a network and say, oh, this is the emission from this device, wrong, it is not. What you measure is always a combination of the device, the network, and all other equipment that is connected in it, what you're not capable of controlling. So the definition of primary emission is the emission that a device has when it is connected to a clean network when nothing else is connected. That's what we call the primary emission. Now, in practice, there will be also a grid connected to it, and this primary emission will also might be affected by other devices that are connected to the network. So in this example, we have one device with a certain emission, this is I superharmonic 1, a certain impedance, so this is the simple Norton representation of the device, the network, and another device that is in this case just an impedance. If you then look at the primary emission of device 1, which you measure at this point, this is not anymore just this value. It is the division of the current through the different impedances of the device itself, the grid, and the secondary device. And in this case, it's still quite simple. But that second device, if you're going to measure at that point, you will also see a part of the emission from device 1. So this emission will start here, flow through the internal resistance of the device to the network, but also to the secondary device, which means if I'm going to measure at this point of device 2, I will see the emission of device 1. And you can't distinguish between both. And to make it even more complex, if now device 2 is also a source of some disturbances, if you're now going to measure here, you will always see the combination of this part and that part, the whole equation. And this is an equation with more unknowns than number of equations, so it's impossible to solve mathematically. And this is why it is so important to test equipment on networks without additional devices. So not just in the grid, but make sure you have a network you know with a clean voltage source, for instance, and do your test there. And that's a way to cope with the difference between primary and secondary emission. Now, it's also something that I saw in practice. So this is a figure where the emission of two electric vehicle chargers is plotted with respect to each other. So this is the emission of device 1 and the emission of device 2. And it looks quite strange. Where are we looking at? This is the combination I was just talking about. So if just device 1 is active, you see this emission. It's just emission from device 1. If just device 2 is active, we see just the emission of device 2. But if we activate them both, we see something else happening. And there's a whole wide spread of possible emission values that might be caused by device 1 or device 2. It's not a linear combination. You can't add them and get the result. So there's something else, some interaction happening there. And this is a challenge we are dealing with in practice, because if you put multiple identical devices next to each other, this is what will happen. And you can't tell beforehand what this emission will be. So that's something you need to test. Now, we talked about emission, how emission from two devices can interact and cause any kind of strange phenomena. But this emission from a device is also not always constant. So to make the total picture even more complex, we're going to add more variables to the equations. If we have a device, for instance, an electric vehicle charger, now you have them all over here, of course, and we connect them here to the network, and we measure what the emission will be. We get a result. So, we know what the emission is. Let's put it in the field. Everything is within the limits. But if we then put the charger in the field, the emission you get from the charger might be totally different. And this has to do with the fact that the emission is also dependent on what you put into it as a voltage. So in this example, we have this is what we call a complex diagram of a harmonic voltage in this case. A harmonic might occur at a certain amplitude, so a few amounts of a volt, and a certain phase angle. So anything between in phase to the fundamental to totally out of phase, and any random value in between. So using a source that can inject harmonics at different amplitudes and different angles, you can get an idea of how the device will react in certain grid environments. So that's what we did in the research. And what was seen, that this emission that we first thought was constant, at this point is not constant anymore. So dependent on the angle of the harmonic that is injected and also the amplitude, the emission changes between 3 and 4 amps. And so this means that dependent on what is there in the background voltage, harmonics, also changes the emission of the device that is connected to it. And not only at the voltages we inject, but also at other disturbance components that are there for this device. So this is looking at one side. So in the case of the charger, we have the charger connected to the network. The network is an AC source where something can change. But this charger is on the other side connected to a vehicle, a battery. And this battery is not always at the same state of charge. It might be different vehicles. So what the charger will see at the DC side of it will also change depending on the type of vehicle connected, the state of charge, all these kind of different things. And this is also something interesting to look at. So in this part of the research, looks at the operating conditions. So I made a whole graph of for a charger that is capable of doing all the way from 500 volt to 800 volt over different output currents. You can make a whole table of different operating conditions where the charger will or can work at. And if you then test the charger for the different operating conditions, you will as well find that depending on what is there on the DC output, so the type of vehicle, state of charge of the battery, that the emission on the AC side will also change. So this means that there are different factors that contribute to the emission of a device where you have no control over in practice. So this means that it is very important to test all the different kind of devices for not only different grid conditions, but also for different operating conditions. Now, sometimes the results look very linear. So in this case, it's a quite linear plot, which is really easy to model. But that's not always the case. So in this example, I used a linear model to describe the emission of the charger depending on the DC output power and voltage. Quite easy model. But in practice, I'm sure with all these charges that are over here, I'm not sure if that will always be such a linear relation. So that's also why it is so important to test. Another small example, I will briefly go over this because Thijs already told about it in the previous presentation, the supraharmonic impedance. So this is again the same figure as we saw before, but now I added the frequency dependent part to it, because this network, of course, has an impedance at 50 Hertz at the fundamental frequency. But if we are looking at disturbances, we also should be able to, or should know what the impedance is for these higher frequencies. So, traditionally, looking at cables and transformers, this impedance is quite straightforward. You have an extrapolation of the fundamental impedance over frequency, so that will just increase with frequency. But with all the devices that we connect, it's not linear anymore. So it's more of a capacitor behavior, and the impedance might more look like something like this. Which means that the total impedance of the network will be a combination of both, depending on where you measure, on what kind of device are connected, making it very difficult to determine what, for instance, this current should be at maximum, because the maximum current depends on the impedance. Now, some conclusions and solutions. I was looking at some pictures from Steden, and I found this one. I found it very, very nice. A few years ago, they rolled out new smart meters at Steden and also at the other grid operators. I was not working at Steden at that time, so I'm not sure about the details. But I found this picture of a guy with an electric cargo bike installing the meters at different houses. And I'm not sure if they did the whole region of Steden with this electric bike, but at least the palace from the royal family, the Paleis Noordeinde, got their smart meter installed by this electric cargo bike. And I thought it was a very nice solution to sustaining the renewable image of a company by using electric bikes instead of fossil vehicles. Now, talking about real solutions for the problems we were looking at in this presentation, I think it is really important to test high-power converters, like electric vehicle chargers, for different grid conditions and different operating conditions. It is very important to include also effects of the impedance of the network and of devices, especially for the superharmonic range, to get more insight on what is there in the field. Grid operators should measure and monitor at different voltage levels what is there. And I think the last one, maybe the most important one, is cooperation between grid operators, manufacturers, and standardization bodies in order to achieve an overall understanding of the different challenges that we face and to be able to work on this together. In conclusion, we are in a transition to our converter-based system. So in order to make more use of renewable energy, we need to increase our use of converter-based devices. Like all new technologies, this will also bring new challenges. It brings a lot of positive things for the network, for the whole society, for the environment, but also new challenges. And in order to cope with it, we need to research and test to make sure what is going on. And I would like to say congratulations to ELAT on this topic, because with achieving this new testing system, that's a great step forward in this testing and measurement and to better understanding the different challenges we are working on. Because in the end, I believe that if we cooperate and if there will be standards describing the challenges we are facing, ahead lies a sustainable and a future for everyone. So, thank you.
Thank you, Tim. So we have now a couple of minutes for some questions from the audience. So if you have a question for either Thijs or Tim, please raise your hand and we will give you a mic and you can ask your question.
Ik kan je verstaan, dus.
Hello? Yeah. So in your research, you are still focusing on AC to DC conversion still, also from the existing grid.
Mm-hmm.
And that will continuously lead to superharmonics being an issue.
Yeah.
What about also looking into the DC grids, that we also on the high voltage already start with DC? Is that a topic of research as well?
Yeah, that's a very interesting question. I did not look into this myself, but I think, as we saw nowadays, that all devices are actually working on DC If you would start all over again, so if we were to design the electricity grid at this point, go for DC, sure. But
Different safety requirements though, eh?
there will be, yes, but we can figure it out. But I think at the moment we already have a large electricity system, and it might be some hybrid option between AC and DC systems. And I agree that with DC you solve part of the problems regarding superharmonics, but not all of them. You also move them to higher voltage levels. So what was the problem of the system operator is now the problem of the grid operator. So still the customer can complain about everything, but we move the problem to a different entity. So,
Well, one thing, so I'm being for Vloek, one of the solutions you will always find is separate.
yeah,
So try to separate the components that are sensitive to it from the source. But fast charge networks, you could already think about why not put that on a separate infrastructure. Just a thought.
good question. Thank you.
Thank you. Any more questions? Yes, there's also, and maybe please before you ask your question, state your name and your background.
All right, I'm Roy from North Brabant province. I was wondering, you said it's acceptable to have 5% of at the very start of the presentation, 5% of the grid to be so bad that the 5% of worst apparatuses will have some kind of malfunctions. Are you able to say something about where this 5% of the worst parts of the grids would be? Are they is there some kind of trend on where this would be, or?
Yeah, if we look at power quality as a whole, there's of course different aspects. I think the worst is always at the parts where the impedance of the network is the highest. So that's mostly at long cables, far away in rural areas. If you have a farmer that wants to put PV panels on the roof, with a cable that's kilometers long to the grid operator's station, you get a lot of problems there because the impedance of the network is so high. So I would say, yeah, that also applies for harmonics, for imbalance. At those points you have problems, and if you then put a device there that's not that immune to that, so can't work with very large voltage fluctuations, you get problems at that site. So
right.
It's not that generalizable, but yeah, I think that's a point to look at. Yeah.
Yeah, and in addition to that, looking at highways and service stations at highways, sometimes they're far away from a bigger grid connection, from a onderstation, a bigger transformer station.
Yeah.
So in that case, it will be a long cable indeed going there, and there will be a lot of local energy problems.
Okay, more questions?
Thank you. I'm Mohammed from Allego. I actually had a question about the primary and secondary emissions. Is there a definition for what is a clean network, or guidelines or standards to measure these?
Yeah, I think there are some standards telling how your environment should look like when you're going to test equipment. This also includes a so-called LISN, so that's a device that emulates the network impedance. And there are some standards looking into this, so I think I can give you more details if you will come to me afterwards. Yeah.
Can I ask a second question?
Of course.
So you mentioned the superharmonics can be at higher frequencies, and they're also not multiples of the fundamental. I was wondering if there are filtering devices, or if they're easier to filter because they're at a higher frequency.
Yeah. It is nowadays still quite difficult to mitigate the superharmonics because they are not always at exactly the same frequency, so they might shift a bit as well. And if you talk about active filtering, that's mostly still limited to somewhat about 9 kilohertz. So above that it gets really difficult because you need a really fast responding system to filter it. But of course an easier option would be to use a passive filter inside the device. So if you know the emission is like this, you can filter at the device itself to make sure that what you put into the network is already limited. So that might be a solution which is feasible, I think. Yeah.
Okay. But are there filters in the network, passive filters, or not?
I'm not aware of that.
Okay.
Not for superharmonics at least, no.
And by the way, about installing these types of filters in your charging station, always remember that you're not only absorbing your own emissions, but also the emissions of device 2, 3, 4, especially at a charging hub or some, for instance, where you have multiple charges of the same kind. They're all emitting the same kind of distortion. They might have the same type of filter, but they're also absorbing each other's emissions. So you might need to, well, have a filter with a bit of overcapacity to be able to handle that.
Thank you.
Okay. I have also a question I'd like to ask both of you. So I mentioned that years ago I studied electrical engineering when I started working at Enexis. My first job was actually also the same what you did, but the new devices on the grid were then greenhouses. So of course in the Netherlands we produce a lot of vegetables and flowers, and they are grown in greenhouses. And 30 years ago they moved to a new lighting system, frequency controlled lighting, which also introduced a lot of harmonics into the electricity grid. And I remember from back in those days that it was a very Dutch issue because, of course, yeah, we are big on greenhouses and these modern technologies. So we did not have that many peers to ask and work together with. If you look at EV charging today, all of these charging stations are not only sold and deployed in the Netherlands, but also in other places, not just Europe, but across the world. The vehicles you see here, you see a Kia from Korea, a Tesla from the United States. So this is a very international topic. So my question to you is, are you working internationally to join forces with other parties that have the same challenges as we have in the Netherlands?
Yeah, that's a good question. Well, we're working together, of course, with the DECRA and the CAMA labs, who are also international, with DMV too, of course. They're international test labs, not only focusing on the Netherlands, but Europe and worldwide. But also, for instance, the Joint Research Center from the European Commission. We're also working together with them. They have multiple research locations, like here in the Netherlands in Pette, but also in Ispra in Italy. We're also working together with them to also, well, further this research on superharmonics, power quality, the charging stations in general, just e-mobility in general, actually, and helping to get these devices further. Does that answer your question a bit?
Yeah, but maybe also the cooperation with the Nordics, with the Norwegian conference that they have every year.
Yeah. At the moment, there's also a conference going on in Norway. Regarding e-mobility, and we're also. You mean the skill project, or yeah. We're also in the skill project, for instance. And the skill project, it focuses on bidirectional charging and, well, the RFD grid codes. Once a device is feeding back energy to the grid, it also needs to comply to new kind of rules. The RFD grid codes, like any device that would deliver energy back to the grid. But well, for vehicles, that's a new thing, of course, and for chargers, that's a new thing, because there's a new, well, world opening up. For these manufacturers to have these devices tested on these kind of compliance, and also being able to change these kind of settings, because the RFG grid codes, they're also different within the different European countries. There are some small tweaks, and they can also change over time. So if a vehicle will be able to do vehicle to grid, it will also be able to, must also be able to change its exact behavior per country. Well, and this, at the moment at this conference, indeed, it's focusing also on bidirectional charging and also these kind of challenges. Like, okay, how are we going to make this possible? Together with, well, with the testing organizations, with the standardization organizations, with the vehicle manufacturers, the station manufacturers, etc.
Any other questions from the audience? Mr. Kreuter has a question.
Thank you. Björn Kreuter from DECRA. Thanks, Thijs, for triggering that question. And actually, it will go to you, Tim. He just spoke about bidirectional, and you are a kind of like grid operator. And of course, people start to think about AC bidirectional.
Yeah.
So what exactly would be the position from your side? Because that also would produce harmonics and supraharmonics. Is
Yeah.
there already a clear idea? Can those vehicle AC be directly connected to the grid or not?
Yeah,
For
I think
discharging?
it's really something new for the grid operators, like electric vehicles were or are still for the past decade. But for a vehicle to grid, that's again a new challenge. And I know that later this year there will be a new grid code on the RFGs that hopefully also says something about the vehicle to grid. But we are still, as grid operator, looking into what should we expect from it and how are we going to deal with it? Because if everyone is in the end injecting energy into the network, this can of course benefit the network a lot. We can solve maybe locally some problems with it. But I think it's important that we as grid operators stay behind it and look into it that is not at first for the network.
What I can add to that, to your question, Beat, so on May the 29th, looking at Celine, if that's the correct date, at the end of May, we will have here at the ELA Test Lab a symposium about vehicle to grid. So if you're not familiar with the topic, indeed, what has been mentioned is vehicles will be capable of providing power back into the grid and in that sense becoming generators. And of course, one vehicle feeding back into the electricity grid is okay, we wouldn't even notice. A fleet of vehicles, okay. But if at a large scale, fleets, trucks, a lot of passenger cars will start feeding back into the grid operators will need to accommodate for that and calculate that into their grid operations. There is a lot of discussion, of course, because this is a new topic. It's quite complicated and it brings together the OEM industry that has never dealt with grids before and the grid operators who have never dealt with the OEM industry before as well. So we have a very interesting conference. We don't have all the answers, but it will be, you are all invited, of course, also to join there. And we will dive more deeply into the topic of bidirectional charging, vehicles becoming like power generating modules, and what would it mean for the grid and the grid operators.
Well, hi everyone. I'm Tycho. I'm the student who is continuing Tim's research. You mentioned that the V2G, vehicle to grid, is like a very new challenge. But when we look at a DC source that we have to convert to AC that's very distributed, I'm very reminded of solar panels. So aren't the converters very similar that we would use for V2G that we also use for solar panels right now? So yeah, how is it a different challenge this time?
Yeah, of course, the converters that are in the vehicles are bidirectional, the PV inverter is not. And this means that often the topology of this inverter, or converter I should say, is also different. So where the PV inverter is meant with the solely purpose of injecting current into the grid, the electric vehicle charger can do both. This also means that the disturbances might be totally different and depending on other factors. So yes, just looking at the amount of energy or power injected into the grid is totally the same. But from power quality point of view, it is totally something different. So that's why I think it is important to study this again and to put research into this topic to see if it is like the PV inverters or probably something behaving else. Yeah.
Thank you.
Any more questions? Looking at the time, I think we are now headed towards the coffee break. So please grab a drink and we will come back here at 2:30. Okay.
Top.
Okay, so we will continue now with the presentation, a very interesting presentation from Beat Kreuter from DECRA. And I'd like to invite you all to join us here again at the presentation area. And I'd like to invite Beat to the podium.
Okay. Yeah. Is it magic? Yeah. What's the magic? This one? Yeah. That's magic. And the other magic? Oh, that's the magic. Okay. I think we can slowly start. So I hope almost all of you are aware that there was a new standard published, especially for DC charger. It's actually not new, it's in a so-called edition 2. So that's the IEC 61851-23, specifically for DC chargers. That standard has been published in December last year, so it's just a couple of months. And I'm not sure if you have exposed to this standard. If yes, then I actually have a question to you. Do you believe that standard is going to improve the reliability, interoperability, and let's say customer experience charging electric vehicles for DC charging, of course? So maybe once we are through this presentation, I would be more than happy to hear your feedback, whether you actually think it would improve. Now, a part of that IEC 61851-23, the good thing is that also the new US standard SAE J1772, which has been published in February this year or January this year, is pretty much aligned with the IEC 61851-23 when it is about DC charging, so the characteristics, the performance requirements for DC charging, which actually is a good thing. And, well, why do we actually need to talk about that? So, well, it's always the same story. If you look at these statistics and press releases here on the left side or on the right side, left side from your side, that's more in United States. The majority of charging stations in the US appear not to work. In Europe, we have the German government, which is every month publishing a statistic where it says how many of the attempted charging sessions were successful and how many of the chargers actually were available. So if you look at the top, it basically means that about 8% of charging sessions in Germany are terminated within 2 minutes. So that means they are not successful. And the lower part of the statistic shows that about 5% of the charging stations are not available, so they are down. Again, that's a statistics which is being published by the German government. Now, we have those two new standards, both to describe requirements, performance, reliability, but also interoperability requirements for DC chargers. They are not new, so these are updated versions. The -23 version, as said, is edition 2. So the first edition has been published in 2014, so it's just about 10 years ago. And of course, many things have happened in the meantime. I think development of chargers, DC chargers in particular, has sped up. More and more power has come, the voltage has increased. The old standard basically talks about DC charging up to 500 volt. Now we know that 500 volt nowadays is no longer enough. So a typical passenger vehicle can go up to 900 volt. And when we talk about megawatt charging, we go actually very close to the limit of the low voltage range, as we call it, which is 1500 volt. So it was about time to actually make an update of both standards. I want to focus on the IEC. What usually happens if we have an IEC standard, that IEC standard will be transferred also for Europe into a harmonized European standard. I have been told that this will not happen with this edition 2 for Europe, so that IEC 61851-23, it appears will not be a harmonized European standard, which I think, if it's correct, is a disaster, because that means for the next 3 years, for Europe, the so-called harmonized standard still will be the old version 2014. Maybe you also have heard something. The reason for that apparently is that those so-called HAS consultants, which the European Union now uses for looking whether an IEC standard could be an appropriate European harmonized standards, they concluded that this IEC-23 does not meet the requirements to be a harmonized European standard. So that actually indeed again would be, in my opinion, a disaster. Okay. What are the differences between the old version, so the version from 2014 versus the version from 2023, so the edition 2? The structure basically has been aligned to the -1, which is kind of like the basic standard for charging electric vehicles. So in particular, it has been aligned to the current 2017 version, which in this case would be the edition 3 of that IEC standard. Electrical safety requirements have been revised and also a bit aligned, and it is today possible, let me see if that works, to actually test the electronics of the inverter based on this standard, IEC 62477, and or also based on this IEC standard 62368, which maybe some of you know is the standard for telecommunication equipment, which is a new type of standard because it looks at the hazards which could be potentially inside that product. So it is a hazard-based safety approach. That's also a good thing because DC chargers in many instances have new technologies inside where there is nothing basically known inside the standard on how this should be evaluated, and if you do it based on a hazard-based approach, then even if nothing clearly is described inside the standard, you will be able to come to a conclusion. So, also one of the major changes is that test methods for checking conformity to the stated requirements of that edition 2 have been added. That is something what the old standard was completely lacking, so there were no test procedures described, nothing, there were just requirements but nothing on how to test them against. And that is now different, so the edition 2 has very clear testing requirements. Some of them we will discuss a little bit later. So generally, of course, also other charging standard systems are being described there. So like here the Annex A is the so-called System A, which would be CHAdeMO, and System B, which would be the GPT standard. Our focus of that international standard will be on the CCS part, so which is the so-called System C. All requirements, performance, quality, and reliability requirements basically have been updated. So not only for the CCS standard, which is being used in Europe and United States and other countries, but also for CHAdeMO and GBT. Oh, that was the wrong way. Yeah. There is also a slight difference inside the definition. This you basically can see here. So typically we were referring to a charging session when we were discussing about plugging in until we plug out. So the new standard now actually talks about a coupling session and no longer a charging session. It will take some time to get adjusted to that, but that is okay. What also has changed is kind of like the description of controlled current charging, controlled voltage charging. So that is now called controlled current mode and controlled voltage mode. So this is some essential functionality of the DC charger. And we also have now clear specification on what we call the side A. So side A is the grid-facing side, and the side B is the EV-facing side of chargers. It is important to understand that when we go through that standard, which also, amongst others, has almost 3 times as many pages as the edition 1. We have to clearly understand what requirement does apply to the side A, so the grid-facing side, and what requirement does apply to the side B. Again, also for the next couple of minutes, we will focus mainly on the side B. Also something what has been introduced is rated boost current. So that is a current which a charger can sustain for a short period of time without that any kind of temperature limits are exceeded. So that is now also a part of that standard. When we look at functional requirements, they mainly have been remaining identical. However, there are 3 requirements which have been added. One of them is the maximum allowable current. Another one is voltage limitation at the side B, and a shutdown of the EV supply equipment. Shutdown means, for example, normal shutdown or also emergency shutdown. It will not be possible to give you all the differences, but I will pick out some essential differences, and I also will give you some examples why it is core to make sure that actually the industry should try to comply with those new requirements. So one of the first one is the output current regulation, which has been aligned, improved, and also, of course, taken into account that in the meantime, output currents can be in excess of even 600 amps. Also, again, that would be only for a limited time. So in case, for example, for this rated boost current. So we do have new limits for 3 ranges. That means when the current is below 5 amp, between 5 amp to 50 amps, and everything what is above 50 amps. And again, that's about the accuracy or to be aligned with the so-called EV target current. Certainly, you can ask yourself the question, does it matter? And yes, it does matter. That's what we have found during a charging session. And you can see multiple problems here. So, first of all, I think I have to do it here. First of all, the target current was a straight line at, here in this area, 277 amps. So the vehicle requested exactly always the same current. And when you then look on what actually has been measured, then you see here something, quite a huge range between the maximum current and the minimum current. Needless to say that this kind of fluctuation or ripple current or poor control of current also produces a lot of supraharmonics, as we just understood before. Not only does it produce supraharmonics, but of course it also produces emission. So it's not good for the grid, and it's surely not good for the charging, right? here in this case, as we can see, I have to say the charging session was successful. So the electric vehicle was able to take that for whatever reason, I don't know. But we were actually asked to do measurement because on this DC charger, from time to time, charging session have stopped for no reason. We were not able to actually duplicate that, but we had a we suspected that there is something not correct. What we did, we introduced some filtering for actually measuring the current, and we still did see that the current here is fluctuating quite a lot, even if you introduce a filter. So that means we already eliminated the high frequency part, so to say, but we still had a lot of fluctuation here in this area. And again, if you look at the target current, that basically is a straight line, so the electric vehicle always asked for the same current. We were able to obtain, because we were not able to duplicate that, but we were able to obtain PCAP files from another electric vehicle, where we basically only could work with the values which are actually being communicated during a charging session. So, I think I have to do it here again. And of course, we saw that something happens here. So when you look at the EVSE present voltage, that's the voltage which is being measured, and you also look at the current, you see that there are negative peaks. And what we found, that once such a peak here occurred, that the charging actually stopped because the electric vehicle was sending a message and saying, okay, something isn't right, and basically provided this full message, and the charging session has been terminated. I think in this case it was about after roughly 3 minutes here, as we can see here. So this kind of charger, which does not comply with output current regulation, at the same time also doesn't really comply with ripple current, they are in the market, and of course there might be just simply the reason that charging sessions prematurely terminate and the user doesn't really know that. So that's really something what we as an industry have to improve. Okay, so that would be the voltage current limit. So in principle, what we did see before, there are 2 issues. That's the current regulation, but also the voltage and current limits which are exceeded based on the new standard. Other issues which are being addressed inside the new standard is the temperature monitoring. So that is also very important. And what we have now, we have requirements that when the temperature is exceeding 90 degrees centigrade at the connector for more than 8 seconds, the EV supply equipment, so that means the charging station, basically should reduce the current or trigger an error shutdown, terminate the session, right? That is also something which was not the case before. And there has been an extensive test case defined to check for compliance against that requirement. So essentially the charger will be operated for a period of 1 hour to make sure that either it stays below that limit, or if it exceeds that limit, that it basically shuts down or reduces the current before those 8 seconds have been reached. That's over temperature protection. What is now also defined is that chargers have to be tested at 40 degrees centigrade with, let's say, the rated requirements, so at rated power and rated current. Also something which was not the case before. Okay, another essential improvement, that's the cable check feature. The cable check is here to ensure that the safety, before the charging process actually starts, that the safety is ensured. So what we do during the cable check is to make sure there is no isolation fault or whatsoever. Also, there, test cases have now been defined to check that.
there are also two approaches to the cable check voltage. So, for example, if the electric vehicle maximum voltage is below 500 volt, then the cable check voltage is either 500 volt or the EV maximum voltage plus 50 volt, whichever is higher. And if the electric vehicle voltage is more than 500 volt, then it's either 1.1 times the electric vehicle voltage or the maximum of the charging station voltage. So we actually have varying voltages for the cable check. And again, it's important to understand that this is a safety test or a safety check. And also there, of course, we do see a lot of problems. We see problems that, in fact, no cable check is being performed, or the cable check is being performed at wrong voltages. So this, I think, here was a good example at 800 volt. So the charge did go up at 800 volt. And this one here, for example, let me have a quick check. What's the EV maximum voltage? Is 825, but we see that the cable check only went to 500 volt, which basically would not comply with the new standard. Other problems which we observed in the market and which now also has been clearly addressed is the fact that chargers sometimes need to shut down for emergency reasons. And one of the more important shutdown procedure is if the electric vehicle initiates emergency shutdown. So if the EV thinks, okay, something doesn't go well anymore and I immediately need to stop the charging. What we have now is we have a so-called reaction time of 10 milliseconds or less. And that's a bit different from before. And what it basically means, within that reaction time or trigger time plus the reaction time, there are about 30 milliseconds to make sure the current is below 5 amps and is below 60 volt to create safe conditions. So also here, if we look, let's say, let me skip that, let's go to this one directly. If we look at what we see on the market, we see times of 46 milliseconds until it actually is triggered, and we have times of approximately 40 milliseconds before the current is below 60 amps, and another roughly 100 or so milliseconds before the voltage will drop below 60 volts. So also that, in fact, could be a safety hazard. Also here, I think that is even more extreme. So the trigger time and the reaction time of reducing to current below 5 amps was like 428 milliseconds, and for the voltage it was about 2 seconds. Too dangerous, very clearly too dangerous. Should not be the case. We also spoke about cable check voltage. So also here we did see many different things. So in this case here, we did have a cable check voltage. But when you look at the time for the cable check voltage to actually decrease to 0 so that the pre-charge can start, you will see that this time is quite long. And what happened is that in that phase, the EV will some sort of trigger a pre-charge timeout. Typically, the pre-charge is very short. And if you are not able to achieve that pre-charge because of some problem with the cable check, the EV basically will shut down and say something is not right. We also did see that on the market, so that we actually have no cable check voltage applied whatsoever. And that, of course, again, should be a no-go, right? Okay, to summarize that, there are many new requirements, and for all of those new requirements, the good thing in this new standard is there is now a way to test them, and everybody would do the testing in exactly the same way because it's all described inside the standard. And again, those tests will make sure that we have a certain guaranteed functionality, a certain minimum level of performance and quality, and of course, still again, what is important, that the chargers are actually safe. And I honestly believe by complying with this new standard and making sure it is tested according to that new standard, it will really help improve the overall situation with regards to unreliable charging. That's my personal opinion. And now, actually, the question to you would be, do you believe that as well?
So thank you, Beat, for your. It's always a pleasure listening to you explaining all this complex matter. And whenever you explain it, it sort of seems quite simple, not that difficult. But I think it's also largely due to the way you present it. I have a question for you, because it seems that the experience that the industry has gathered over the past decade has, of course, led to a lot of improvements, making the whole system more clear and more reliable. The old standard was from 2014, and I think maybe a lot of you back in 2014 were not even aware of electric vehicles, perhaps. So what is the reason that the European Commission chooses not to adopt the learnings from the industry and move to a better technology? And what is the reason why they want to stick to a 10-year-old
I do not really know exactly the reason, but what I understood is it's some kind of formality. Right. And the problem are those so-called HAS consultants, which the European Union now employs, and their job is to check whether a certain standard is in conformance with the essential requirements of all these directives and regulation which do exist. And it seems like those HAS consultants came to the conclusion that that new standard does not address that. And that's why it seems to be rejected, which means the edition 2 will not going to be a harmonized European standard, but we will have to wait for another possibly 3 years for the edition 3, which I honestly think it's a complete disaster. But okay.
Okay, thank you. So I think then it's for the industry. I think this makes so much sense that hopefully most industry vendors will understand that this is much better way to go, and will not wait for European or Senelec implementation and just do what makes sense. Okay, thank you. Very quick question for Beat before we move to Erik. If not, of course, there's always questions after the demonstration, I think. So thank you, Beat. Applause again for Beat.
Thank you.
And then next up, Erik. There you are. Please come to the stage and take us through the world of high power charging. You know, KEMA Labs is famous for its high power labs.
Okay. Thank you very much, Sonneke. So I'm Erik de Jong from KEMA Labs, and I will be telling you something about the future. If my slide will continue. Uh-oh. Do you know what I'm doing wrong? Help's on the way, yes. Is it on?
Can you do it again?
No, it works.
Yeah, it works.
Thank you. The marvels of IT. I'll start again. Good afternoon. I'm Eric de Jong from Kima Labs. I'll be telling you a bit more about what we are doing here, about the testing of the future of EV charging. For me, it is taking the new definitions of the new standard side A. That's the most important part, the grid side. All the problems with side B has been tackled, so I'll be talking more about the side A in here. And especially the high fidelity testing that needs to be ensured as powers go up in EV charging. I'm running through a few topics here, as you can see here, laying down the field, looking at products themselves, looking at systems, and how we can look at testing in particular of systems as we go forward with high power applications. And then there's something called power cybernetics, which has been coined a few years ago, which we want to apply in the EV charging world as well. And I'll quickly run you through that as well. So without further ado, we plug in the battery and start charging. The introduction itself, Kima Labs. Kima is a well-known part of Arnhem for more than 100 years already. We are actually 6 kilometers from here, downriver, which is the fastest way of getting between us, although no boat connection yet. Maybe an opportunity for electrical boat service to shuttle us up and down. As you can see, there is our testing facilities, our laboratory complex here in Arnhem. Kima is part of a bigger Chasey group, multinational. This is our Arnhem campus. We have more in other parts. This is one of the 2 parts where we do tests on electrical vehicle charging equipment. And you see there are also more labs that are more classical and intended for grid components, transmission distribution equipment. So you see a big short circuit laboratory, which Lonneke mentioned is what we are known for, the largest short circuit lab in the world still. There's a high voltage lab for dielectric testing, and then there's the flex power grid lab. That is the lab I am from, and that's the functional testing lab on grid connected equipment, which usually houses power electronics, but we're not a power electronics lab, but we see them quite a bit. And of course, everything that you see here and what we're working with on a day-to-day basis is grid-connected power electronics. So that's our functional testing facility that I will mention to you as well. This is already a picture I've been using a few years, and it's still applicable today. It's from the IEEE. It mentions the ubiquity of power electronics. And what does that mean? It means power electronics is finding its way into all aspects of our electrical and energy power systems, into our lives, our daily lives. Here it shows where power electronics is being used on transmission level, distribution level, household level, consumer level, product level. And of course, what we are talking about here is the AC chargers and of course the fast DC chargers with the power electronic conversion happening in them for charging. And at the end of May we'll be hearing a lot about discharging batteries into the grid or any other application. All done with power electronics. So power electronics itself is an enabler for that. We can't do without, we have to make do with, and they have some characteristics we have to live with. And harmonics is one that always pops up with these type of guys. There's technology advances in that brings us new challenges and shifts us into another domain, like super harmonics. But it also provides us the functionality, the flexibility that we need and we want to do the functions that it's intended for. So we can't do without. And we don't want to do without. We just need to tackle the problems around it. In this landscape, we've been seeing it for fast charging, of course, with the AC charging that we've seen, with just a plug denoting the whole domain. It has come up before as well, the 3 main systems, A, B, and C, for CCS 1 and 2, the CHAdeMO 1, and GBT. And what we are moving towards for the electrification of trucking, transport, larger vehicles is, of course, the MCS. With a, for me, relatively small plug for the powers associated with it. I have had the opportunity of working with one of these, and it is really small, surprisingly small for the power if you know what's behind it and what it's conducting. But that's what we're heading towards for electrification of transport, for the trucking sector especially. it's not just that, but we can see a lot of this happening on other levels of grid compliance as well. So we're trying to also bridge the gap with knowledge from other domains, grid-connected applications, generators, requirement for generators on wind, solar, all these type of applications that have been here maybe a bit longer, maybe a few years more matured. Lessons from that applied to this domain. If we look at the product itself, building it from the bottom down, and the more confidence that we have from decades of understanding, testing, and research, we of course start with the AC charging that started off first with testing according to, there we have it, the number soup again, a lot of IEC standards. Well defined, more mature, you know what you get, you know what you're getting yourself into. Here I see the strategy for ALAT as well is our job is almost done with AC. It is known, the challenges can be tackled, it's manageable, let's move on, basically. But just to show you what this means, it's not just electrical testing that we are always, well, at least for my domain, talking about the functional parts. There is safety, there is climatic, there is mechanical testing. There's a lot of aspects encompassed in these standards that you also have to take care of. It's not just unlocking the functionality and using the device as is. And this has taken a lot of years to establish, and we are building on that foundation going forward. So with testing for the commercial parties here, the next step is certification. That's a whole different ballgame. And that is where also accreditation comes into play. And for the well-known standards, also our company has the accreditation to do the certification and provide the market with the paperwork you need to get onto the market. So for the AC testing on our sister company in Milan, Chesi company, and here the MID here in the Netherlands with the Raad van Accreditatie being our accredited body here for the MID. These tests themselves, what does that enclose? As mentioned, it's not just electrical testing. So there's climate testing, there's a whole lot of abuse being done on the devices unpowered that it needs to survive. You can imagine what all those tests entail, freezing it, salt, mist, all these things, long duration tests unpowered, which you have to do. There's mechanical tests, ingress protection is one of them. Impact protection, the IK factor is also a very important one, especially if the equipment is out in the public domain. How does it get abused and how can it handle that? So that's also a part that needs to be done. And then mechanical stability is also part of that. Electrical safety, that's the one we usually talk about. How safe is the system when you're close to it, when you're touching it, when you're around it, when you're working with it? How fast is it to be depowered? All these things are unpowered. And then of course the most magical one, the EMC tests around it, where strange things happen and you have to have strange solutions to solve it before things work. Or that's how it's perceived at least. But there's method to that madness, of course. Then there's also the RED directive from the EU that also says that if you put something into the market, you have to comply with the radio emission directive. That also has its own rules and regulations. So this basically sets the scene for the whole lot of standards, directives coming together for something to be tested, certified, at least on the market, and then hopefully work. Apart from that, there's also interesting things that can be done outside of the standards, which ALAT has one part of is the interoperability tests. How do things work together? How do things match up? What can you do with that? Smart charging, an add-on feature onto the device itself. How can that be rolled out? And then some functional testing, usually used for debugging or research on particular aspects of interest that might happen or might not happen that you need to investigate a bit further. So these are also things where a test laboratory such as this and the other competitors come in. If we step up the game to DC fast charging, and I'm talking about the CCS basically up to 350 kilowatts, which is now also enabled here. There you also see the communication interfaces between the car and the EVSE, the EV and the EVSE coming up with, of course, all the standards for those communication protocols where conformance can also be tested. And these standards come from societies that govern these standards. The well-known one there. Also looking at power quality for the bigger units, as it is not an AC charger anymore, power is going up, you have a converter connected, you are looking at grid compliance of larger loads, which has some grid compliance requirements as well in terms of power quality and interoperability of the grid. They're also mentioned here. There's also for the higher power units some nuisance measurements that you have to make, noise, light emissions, especially if things are in the public domain or close to residential areas, things you have to take care of. So that's all mentioned there. And here it's above about 350 kilowatts. For DC fast charging, you have to comply with the same RED for radio emission with that directive, so you're not excluded from that either. So you have to take into account all these aspects as well. Then, building up to the next level, it has been mentioned here as well, the megawatt charging system. This is when things become really interesting. For me, bigger, higher power is still better. Where now the confidence level is also decreasing from the AC where we know everything, the DC where we're getting grips on what's happening. With megawatt, we are still, I would say, in infancy. There's the organization looking at defining the standards for communication, the MCS standard, who brought out a white paper with all these normative references in there that should be included in the standard that should come out, but it's not here yet. So there's a lot of formative discussions now getting into what will be the megawatt charging system. You can see a photo of the plug on your right-hand side and a long list of standards which will be incorporated in some way or another into this MCS system. So that's what is ahead of us. If we look at, we go from products and we go to system requirements and we look back to the MCS, you see the same plug here. You now see that we are now handling possibly theoretical powers of up to 3.75 megawatts, 3000 amps DC, 1500 volts has been mentioned as a safe low voltage value. These are considerable amounts and deem respect from these components. And of course, the idea behind the MCS, or one driver behind it, is to be able to respect drivers' drive and rest times with electrical infrastructure, giving them the opportunity to rest and charge their truck in the same time, which means bigger batteries need to be charged in less than 45 minutes. And that's where you end up with currents exceeding 1000, 1500 amps to be able to charge the batteries within coffee drinking and bathroom break time. So the drivers are there, the motivators are there. Now the technology should support that. And of course, it should be grid connected, and from the energy point of view, should be able to handle that as well. Not just one charging station, but you can imagine if there is a truck stop, it's not just one truck stopping at the same time. For anybody who has traveled through Germany on leisure or business travel, if you are at the truck stop, there's many at the same time. And if this is the future, then there's a huge challenge for the side A part, grid connected side. So that brings us from what have we done before, which has been focused on component testing, where we have standards that are there, clear, harmonized or not, but are being used, where we can do testing in facilities like this, with or not certification behind it, to show that it complies to a standard. And that's great, and we should be keeping on doing that, because that gives the quality of the product that you have into the market. But with these bigger systems, the risk is that that's not enough. And when you look at what needs to be done, is that this needs to be included into a system level testing, where not just one product is in the system, especially looking from a grid point of view, but multiple systems work together and need to be able to work together. So you have to do system level testing to show interaction between similar units, different units, not just interoperability from the user point of view, but from a grid point of view. Can it be sustained? Can it do everything it needs? It takes a different approach. You can't just base it on the individual product or component standards anymore, but you have to consolidate that, do system level testing, higher level of testing, but if you do that correctly, you can say that it's fit for purpose, which is a very specific requirement instead of a general requirement coming from general standards. And I think that's the message that I want to say here as well. As we grow up in numbers and in power, the focus is not just on the product testing anymore, but needs another layer of activity as well to get the quality and the usability and availability, what Lonneke also started with today, from our infrastructure, basically. What does that mean for laboratory infrastructure? We have a facility here that can do parts of that. We have our facilities in Arnhem. DECRA has facilities here in Arnhem as well. That can be done. The one I know the most about is the one that I run, so that's the Flex Power Grid Lab, which is our test bench for these type of activities. It has grown out of the grid compliance testing of grid-connected or utility interactive power electronics world, where this is now also entering and combining. So what we have there is a megawatt scale laboratory with some tools to be able to create the boundary conditions to do product testing, but also allows you to do the system level testing and interact with multiple applications. So what you see there is a very small version of a single line with all the tools and the gadgets that we have. What we have in there just on a high level is the high voltage, high power AC grid simulator, building block, one of the puzzle pieces to emulate the AC grid you're connected to, give you the fidelity, the high fidelity that you need on the AC side. We also have, since the opening here, updated our system with low voltage but higher bandwidth amplifiers, and that will get us into the next chapter, which I will tell you about, where you go from the 2-3 kilohertz bandwidth amplifiers to 10, 15, 25 kilohertz, adjusting with the requirements and the technology increase from products. On the DC side, we also have the same environment, as you can see there. More than 1 megawatt bidirectional DC supply that you can use initially as a PV emulator here, but with full VI characteristic curves and being bidirectional. It can also be a battery emulator, which we have done already. So that is the other end of the charger on side B. You have to give the charger opportunity to charge into something that's hopefully not a battery, because for testing batteries are time intensive and needs to be discharged. So an active bidirectional load is preferred to reduce testing times. And for some aspects, you just have to take care that an active source and an active charger working together do not interfere with each other enough to void the test results. That's where the experience from the test laboratory comes in, to know when to apply a tool and when not. But these are the power levels that we have available, and as you can see from the MCS growth that can be foreseen, it's too small already. And that is what brings us to how do you keep up with accelerated market trends in an asset-heavy environment without building a new lab or building bigger, bigger, bigger every time and always looking behind. And that is what brought us to believe that instead of going bigger, bigger, and bigger, go smarter and then have the tools to facilitate the smarter approach of testing. We call it power cybernetics, and the idea is simple. Emulate what you can without avoiding or nullifying the results of a test. So what we embrace here is hardware in the loop, power hardware in the loop, with real equipment in the middle, and emulating all the boundary conditions as far as you can with the high fidelity signals that they require, so that you can draw conclusions from the results, the interactions, and the aspects that you are testing. Here you can see a grid view of how that could be, where you have equipment and the test, and all the boundary conditions, also from communication to backends, all these aspects are connected to it and communicate in its own time domain the correct values to give it the correct impulses it needs to excite a certain working point and condition for testing. This, of course, can easily be applied, reapplied for the EV charging, the DC fast charging situation as well. emulating the DC side, emulating the AC side, and if you're in a climate chamber, at the same time also influencing the climatic conditions around such a device. It gives you multiple levels of freedom that you can use, but also the opportunity to get the device that you're testing in unique operating points. And for climate chamber, it's not that fast, but you can imagine for electrical interfaces, the bandwidth will just increase as switching frequencies and functionality of the devices increase. And you have to stay ahead of what you are testing, of course. So that's the idea of power cybernetics that we are trying to embrace here for what we see as the future of EV testing. To give you some insights into that, the hardware in the loop, for those that do not know the concept, is quite easy to understand. You have a real world component, you have a virtual component that's modeled, and you have to connect the two together. And it sounds easy, but that's where the complicated part is, how to make things believe that they're connected to something that doesn't exist. But if you can do that correctly and nicely, then you have a tool that gives you more reach than a standard dedicated test facility would. And that gives you the key to do more with limited amount of resources, space, area, and budget, of course. So that is for me. You can see the battery's been charged in this session alone. Just a few more minutes to draw some conclusions on here and perhaps pose the last question. So you can see that I tried to convey the message that product compliance to standards is still important and will be important and should still be done. But we have to think for the next step as well on system level testing to show fit for purpose. And the more detailed you can do with the purpose, the more dedicated models you have that you can put into a hardware in the loop situation, the more confidence you can entrust onto the results that you get from such a system of that. We think power cybernetics is the future for tackling this ever-growing problem that's hitting us, to keep the market alive, to keep the quality in the products, and in the end also do certification based on something like this, although that is still a bit further on. And for now we see MCS popping up. I saw the ELA timeline 2025, 2026. I hope we can make major steps in that. But my question for test facility, of course, is what's next? Because that's what we have to prepare for now to tackle and be ready for those challenges in the market. And with that, I conclude my presentation now. Thank you.
Thank you, Eric, for your great presentation. It is great to see that Kima Labs is focusing on this high-level, high-end testing. And it's a great addition, not just to this conference, but I think also to the area that we are here in Arnhem, that you do the work that you do. For now, I'd like to invite back on stage Beat. There you are. For a round of Q&A before we go to the next part, the Keysight presentation, and of course the demonstration of the system behind you. So, Beat, Beat is coming to the stage. Yes, so same question as before. So is there anybody who has a question for either Beat or for Eric? Thijs here as well. We will open and we'll...
Great, thank you. Hey, Eric, a question, because while you have a great system, you're building up a great system, and I'm thinking, like, we're also talking a bit about superharmonics, of course. Is the system also already ready to also, well, integrate these superharmonics in the system, test the immunity on that, or is that in the future plans? I'd love to hear that.
Great question. It is part of the plans, but it is not ready today, because as I mentioned, the amplifiers that we are working now that can do the power part is limited to 25, 30 kilohertz. If we're talking about 150 kilohertz or higher, your bandwidth has to be at least twice that to be able to create anything. That is something that's out of spec of what power amplifiers can do directly, which means you have to think creatively about injection instead of creation from start. And that is something we are taking into account, because that needs to be done. From other domains like EMC, the injection of signals is already more commonplace. So now these worlds have to combine as well. And we're working with that, but at these power levels, it's not something you do in the afternoon. There are aspects to consider and and consequences to take into consideration as well. So yes, my wish list of things that I would need is much longer than I think my work is left until my retirement. So there's enough to do, and this is part of that.
Yeah. We should work together on that, because that's also our challenge, of course.
It's 6 kilometers away.
Okay, any more questions? Now is your chance. Everybody is eager to venture to the demonstration. I have one final question before we invite Keysight up to the podium. So Kima and DECRA, and I also believe DNV, all to a certain extent originated from Kima. 100, you mentioned 100 years ago.
Well, it's a bit less, yeah.
Yeah, I think maybe you don't know this, but 100 years ago there was this company called Kima, and it grew to become a renowned worldwide institute. Of course, times change, and I think it was reorganized, and part of it ventured into kept the name Kima, part combined with DECRA from Germany, part combined with DNV, which is, I think, Norwegian. But still, it's great to see, at least from the ELAT perspective and the grid operator perspective, that in the end, where the e-mobility testing is happening is still around this Dutch area. And I think it's an asset for the Dutch industry and also for Dutch regulators that we have such high quality and world-renowned institute all together. So one of the things that ELAT is also doing and planning to extend is to work together in this region, combine all these qualities, all these facilities. Because if it's one thing that we want you to take away from all these presentations, that is, it's a lot of work. We love this because this is what we do, but it's a lot of work and we need to do it in a couple of years, at least a decade, because we all want this transition to happen sooner than later. So the more we can work together, also referring to the question from Thijs, but the more we can work together as grid operators, ELAT, DECRA, Kima and DNV, the better, I think, for everybody. Okay. Thank you for your presentation. Applause again. And I believe next up is... there you are. Yeah, ooh, you have something nice to show us.
I brought something with me, yes.
Okay, please come up to the stage.
Perfect. So, audio is working, perfect. Okay. So, yeah, maybe I start already. Hello together. My name is Wolfgang Kalthoff. I work for the company Keysight, and I'm working in the business development department, and I'm especially taking care with my team for the charging technology and grid edge test solutions. So happy to be here. My topic for the presentation today is market trends and solutions to test EV charging technology. Basically also under the umbrella of the event, which is future of EV charging. I have prepared a little agenda for you, so basically to answer the question, why is the EV charging interface testing important and necessary? I hope that after my presentation you can give the answer by yourself. I would guide you through the evolution of the EV charging use cases from the start of the e-mobility to where we are now, and also guide you to the evolution of the physical charging interfaces, so what happens to the connector from the beginning to now today, and then also share a little insight about the CCA's protocol evolution, and also would like to talk about then, in a summary, about the technology trends in EV charging that we currently see, and also would like to give you a little example about the MCS standardization roadmap. I saw already in the previous presentation that a lot of standards were mentioned there, so I probably keep it short for you. And then also have prepared a little high-level comparison about CCS and MCS. Where are the differences? Are there differences at all? And also another topic that comes very often in the past weeks is where are the differences actually between CCS and NACS, and what is NACS actually? I will conclude my presentation then with an overview of our portfolio that we have here, also the solution that ELAST is using and also DECRA is using. And yeah, would like then to hand over to the real-life demo, to the hands-on demo, where you then also can ask questions or see the product in action. Okay, when we look at the charging use cases 2015 to 2017, what we see here is basically that we have unidirectional charging AC and unidirectional charging DC. For AC, it was still PWM based during that day, so specified in IEC 61851-1. And for DC, then it was basically DIN spec that was used. Now, if we look at the charging use cases today and foreseeable future, we see, okay, we have in the AC part also now the bidirectional charging included. We have for the DC also the bidirectional charging included. We see a complete new area of application, which is the truck, the mining, but also aviation, so the heavy-duty application here. And then also we see bus pantograph charging or also automated contacting devices such as side coupler and underbody coupler. Last but not least, this will come also in near future, already today available, but on a large scale then in near future, will be then the wireless power transfer. If we look at the connectors that were available back then in 2015 to 2017, then we see that we had for AC in the region US and Japan, AC type 1. For Europe, we had AC type 2. You see on the pictures that there is actually a difference in the physical connector design. However, the pin assignment was basically exactly the same, and also the specification was the same in IEC 61851-1. For GBT, same thing. Also, again, physical different connector for the AC side, but also same technology in use, so PWM-based during that days, and yeah, same pin assignment. On the DC side, we had CCS DC Type 1 in the US. Same technology used like CCS DC Type 2 in Europe, however, also physical different plug design here. For GBT and CHAdeMO, we have the difference compared to CCS that GBT and CHAdeMO is using CAN communication method compared to CCS, which is using power line communication. And also if you compare GBT and CHAdeMO, communication protocol completely different, and also physical design of the plug looks similar on the picture, but is also different and not compatible. If we look at the landscape today, then we see that we have basically three new connectors here. On the left, lower left side, you see the NACS connector. NACS basically stands for North American Charging Standard, and that's basically a new name for the Tesla interface that is around in the US for quite some time. Important to know is here that from 2019, Tesla had a technology change. So before they used CAN, but from 2019, the car was also using PLC technology and also was using CCS protocols. So basically, where is now the change? What is happening in the US market when NACS was announced? Yeah, basically, at the end of the day, it's a new connector. And no change in protocol so far. In the middle, you see the MCS connector, megawatt charging system. We had it in the previous presentation already. That is the standard that should address the new high power and heavy duty application. Goes up to 3,000 amps with a maximum specification and 1,250 volts. In total, that makes them 3.75 megawatts. And I actually brought a sample that was provided by Huan Suna to you. That is basically the intermediate version. So this one specified then up to 1,500 amps. And 1,250 volts, so there will then be a bigger brother that is even way bigger, that then can support up to 3,000 amps. Okay, now looking at the protocol side for CCS, we see on the left side, basically it started with a DIN protocol, DIN 71-1. If you compare, and now, let's check if that works. Works that? No. Could work. Nevertheless, if you look on the protocol specification line and you see the date, then you see 2014 on the DIN edition 2, but you also see for ISO 15118 2014. So basically simultaneous release, or even the ISO 15118 was a little bit earlier. However, as the ISO 15118 standard was very big in scope, was supporting a lot of features, industry has agreed to strip it down and have a little lower specified, or lower in scope at least, version of the standard, and that is then DIN, and that succeeded to be then the global charging standard for the first electric vehicles that supported DC charging. Important to mention is here that there was no encryption, so pretty open, and currently still available everywhere around. And protocol specification, that's also important, is specified in the document DIN 7121, but the test specification, so how to test that the protocol was implemented correctly, is specified in another document, and that is then DIN 7122. This logic actually applies to all the standards, so if you continue then, next level of standard was ISO 15118, now also reality. Important core feature that was introduced to the market was the so-called plug and charge feature. Plug and charge, for those who do not know, is basically the feature to get rid of the RFID card for authorization. So if you drive an electric vehicle, you probably have this pack of RFID card, depending on which vendor you need, and then you authorize if it works. However, this was necessary with DIN, but with the introduction of ISO 15118, if your car or charging station support plug and charge, then you do not have to need to use your RFID card any longer. You simply can plug your car, your credentials are included in the car, and then everything should run automatically. Also here, important to mention, the protocol is specified in -2 and -3 documents, and the test specification is specified in -4 and 5 documents. On the right side, then, we see the further evolution, and that is probably what we all are here for today, and what we also would like to showcase then during our demo, and that is the ISO 15118-20 protocol, and that has the most important feature to be introduced, and that is the bidirectional charging or smart charging. In addition, there is another level of security added. So from DIN, there was none. For ISO 15118-2-3, there was then TLS 1.2, optional for external identification means, but for plug and charge mandatory. And then for ISO 15118-20, TLS 1.3 is mandatory, and there is then no exception any longer. You see on the standard landscape, and I will not read them out all, that also the complexity with this additional protocol is increasing quite significantly because of the introduction of the new features that come along with -20. Now, looking at the consolidated trends in EV charging that we see since for quite some time is the trend to go always into higher power. Higher power means faster charging, means less waiting time at the charging station. That is basically also still prohibiting a little bit the adoption of electric vehicles. However, this trend continues, so we see that on the passenger vehicle side, we see that throughout all charging standards, so not only CCS, but also in the Asian region, for example, CHAdeMO, but also in the Greater China region with the upcoming GBT 2015 Plus or 2023 standard, but also with the parallel standard CHAoG. Here, high power is addressed. Furthermore, second trend that we currently see is the rollout of the plug and charge feature. So not sure if you already all drive an electric vehicle or that you use already this feature. The vehicles have that meanwhile, or some of the vehicles have that, and some of the charging stations have that as well. Also important is that here is a next level of EVSE CCS certification planned by CharIN. So we hope to get or to make progress that we can go live within this year already. And that incorporates then already the ISO 15118 standard. So far, there is a basic level of charging station certification available. For example, can be performed by DEKRA, but that consists of the DIN standard and the IEC standards, and the next level then will include the ISO 15118 standard as well. Third trend that we see then is really the smart charging, the bidirectional charging. Currently I myself talking about the side from the electric vehicle to the charging station, but there is also a big aspect, and that is where ELAT is especially taking care of what is happening behind the charging station when the energy is fed back to the grid, and that is an international issue to solve, and there's a lot of things to harmonize to make that reality. Okay, just as an example here, the standardization roadmap, it's basically a similar slide that my previous speaker had. What I wanted to show here is that a charging interface consists always on multiple standards, and if something is announced, there is a new charging standard, then basically different groups kick off the standardization of different aspects, and unfortunately they also have different timelines. That brings along a little challenge to define a test system. So usually when there is an announcement, we as test system vendor get the request, can we get a test system for that? And then we need to educate also again that we say, okay, there is certain groups, a lot of things are not yet finally decided, and then we continue to do a stepwise enhancement. So focus on the things that are decided and already final, start testing with that, and then we enhance further the test solution as soon as the decisions are made in standardization group. Okay. In this moment, a big thank you for Hugo and Suna. As I said, they provided the sample that is now going around to the right on very short notice. So once again, thank you for that. And if we now compare CCS to MCS communication, then the question is, okay, why isn't not the same? Well, I don't know the answer basically, but I know the differences. So if we look at the communication method, then we see here, okay, for CCS, it's single-ended communication via control panel line, so power line communication. And for MCS, it was actually decided to go via differential communication via a twisted pair. And also important, CCS is using PLC, as I said, and for MCS, it was decided to use Ethernet, and the standard is called 10-base T1S. That's basically a difference, which makes the standards not easily or directly compatible, and therefore we also basically need to enhance our test system. And actually this decision was kind of a surprise during the standardization as well, and the group that is affected by the decision said, okay, we look at approximately 6 months delay that was caused by the change of the physical layer. And that is a little bit unfortunate, as of course truck charging that has a high interest at the market currently, and 6 months delay is quite a lot of time. The benefit why this decision was made is actually from single-ended communication to differential communication, that the crosstalk characteristic, if you look at differential communication, is way better. Signal calibration is not required, and for MCS it was decided to also use the ISO 15118-20 communication protocol as standard. Now, looking at the Keysight solution portfolio, starting with the hardware solution, we basically drive a modular-based approach. Looking at the application, starting on the upper left side, we have our EV-EVSE charging communication interface tester, in short ComTester. This is a product that is designed for communication test only, so not necessarily power is incorporated here in the testing, but you can do either an emulation test or you can do a complete conformance test for ISO 15118-4-5 or also close to be released conformance testing for the ISO 15118-20. Underneath you see additional accessories that should provide a higher degree of automation during the charging testing. For example, we have a swipe robot that then can hold the RFID card and swipe at the right point in time at the charging sequence so that you do not need to stand up every time. So if you ever saw the colleagues testing or a charging testing, then to disclose that as well, our colleagues made a long stick and glued the RFID card so that they do not stand up. However, we meanwhile have now the robots, have received a lot of requests that if we can do something, and so these are fully integrated. Besides the swipe robot, we also have a push robot that can then perform push operations at the touchscreen or at the infotainment system of the car. So we use some kind of mounting system that you can then position the robots exactly where they need to be. In the middle, you see our major portfolio consisting of 3 systems. So on the left side with the stainless steel housing, lower left side is the EMC optimized version of the charging discovery system, is used to be put in an anechoic chamber without bringing in additional disturbances. So that's also a challenge. EMC testing still has to be done at a certain or under charging condition at a certain charging level, and therefore you need to have a super clean charging station that is not bringing in additional disturbances into the anechoic chamber. In addition, that is the red box. We have the Charging Discovery System Portable series. It supports all charging standards such as CCS, CHAdeMO or GBT, and it supports currents up to 400 amps and voltages up to 1000 volts, and also can support conformance testing for IEC standards, but also ISO 15118, as well as GBT-S CHAdeMO. On the right side, you basically see the bigger brother. It's also here owned already by ELAT. It's called the Charging Discovery System High Power Series. Basically, we have increased the current rating already to 600 amps and also 1500 volts already. And you can see on the right side, there's an additional module available by what liquid-cooled charging adapters can be used. So in total, maximum charging power. If you multiply 600 amps with 1,500 volts, then we have 900 kilowatts to serve. Basically, we are already working today on an enhancement for the MCS parts that are decided. So we also, you saw the sample from our supplier Huber & Suna for the liquid-cooled charging adapter. That can be also attached to this system already. Of course, then you are limited in terms of power or current and voltage. However, the next system generation then, of course, will address also this super high currents such as 3000 amps. Important to mention is that these test systems are CHAR-in approved. So a test system or a test house can use these systems if it is CHAR-in approved to certify DC EVSEs. So already today available the basic certification, but in near future also available then the so-called advanced certification, or extended certification, sorry. On the lower side of the picture, you basically see also that we provide emulators, and we start at low increments from 5 kilowatts up to 300 kilowatts per cabinet, and then we can also switch them in parallel up to the megawatt level so that we are perfectly prepared, and we are basically also the only vendor at the market that controls the whole test system from out of its own portfolio. So most of the other vendors that you find out there, it's always a mixed solution from different vendors. Certain aspects they need to get back to different vendors. Kisa drives the one vendor approach, and that has a lot of benefits, especially when you look at this dynamic landscape, because we only need to talk to our direct colleagues and can solve interface issues, which is easier compared if you approach another company that has then different priorities, etc., etc. On the right side, you see a new addition to our portfolio here as well. It's so-called CCS Charging Protocol Tracer, and that is a tool to capture PLC data either in the field by using an inductive cable clamp or by installing the system either in your charging station or in your vehicle and drive around and then capture the PLC communication data from your roadshow. On the software side, basically similar situation. So we have dedicated software environments depending on the application. Starting on the lower left side here, this is the conformance test automation framework. We support fully automated conformance testing for DIN, ISO 15118-4-5, and in near future also -20 here. In the middle, you see the Charging Discover software. Here we have the focus on the IEC standards, but also on CHAdeMO and GBT. Of course, you can use each software with the same system of hardware. It's simply depending on your application which one is the right to choose and the right point in time. Below, we have also a new addition to our portfolio, and that is the so-called EVSE Smart Charging Emulation software. That's also quite a handy tool to simply enable a quick charging station and do just minor parameter modifications. And this environment already today, and you will see it in the demo later on, supports already ISO 15118-20 protocol testing for either EV emulation or EVSE emulation, focusing on DC and bidirectional power transfer and other aspects of ISO 15118 to follow shortly. On the upper right side, then you see the CCS charging protocol trace viewer. That's basically a PCAP file decoder that we serve here. Comes very at an interesting price level and is definitely a usable tool if you have decoded PCAP data and you want to, if you have encrypted and you want to decode them. So, okay, now showing the solution overview, and what is nice, as I explained already, the one vendor approach is that we have the plan to combine our test solution then at the end of the day to an end-to-end test solution. And that especially becomes interesting when we look at the grid side here, because then we can go from the input completely to the output, back in the grid and back and forth. All our equipment is bidirectional. That means also the total cost of ownership are quite reasonable because you circle the energy in the loop. And so you do not have big losses because the systems are also quite efficient. Okay, that's basically my last slide. And with this, I would like to turn this over to Robert and probably Sven.
Thanks. Yeah, you can hear me. Before we start the demo, I will do some short explanation about what we are going to test and what we will show you. First of all, the demo is behind you, but you can all stay seated. It will be displayed on the screen, and we will make sure you can see everything that is happening. Let me introduce myself. I'm Robert Italiander. I'm an electrical engineer and a technical expert in the ELA test lab. I've been working here since 2022. And I'm a project manager. And actually, my first project I did was the installation of the key site. So I'm quite happy that we can show it to you today. I'm going to do the demo together with Sven. He's there. Maybe you can introduce yourself shortly. Can you put on the handheld, Reen? Yeah.
Can you hear me?
Yes.
Great. So yeah, my name is Sven Gröning, working as an R&D manager by Keysight since 2021 with the acquisition of a company was called Verisco. And I'm actively working also in standardization since 2010, something, when everything started to develop the first test protocol for the DIN standard we have seen today. And today I would like to show you the demonstration back here. I think we have a camera working here together with Robert, how about 15.8-20 implementation can be used with our systems. Coming back later, thanks.
Thank you, Sven. Okay, Thijs already explained why we test, but I quickly repeat it. As you might know, DC fast charging is getting a bigger and bigger role in the charging of EV, therefore also getting a bigger role on the grid impact it makes. We as a grid operator want to be able to measure it and want to be able to know the impact on this on the grid. Therefore we need to measure and therefore we need equipment. We also want to improve our interoperability testing that we can offer. So when we are finding a problem between an EV and a charging station, with the Keysight we can really pinpoint where it went wrong and help the OEMs to improve their products. And lastly but not least, we want to test the newest technologies like vehicle-to-grid, like plug-in charge. Okay, now I'm going to explain what kind of devices we have. The testing system has 3 main devices. The first one is an AC emulator. We need that emulator to, it doesn't work, unfortunately. To make a clean grid, so at the left side you see a grid, can be distorted. For testing the power quality, we need a clean grid. But we also need to create a controlled disturbed grid, like the transients, the voltage sags and swells, and harmonic injection. Right now we can only do that up to the 50 harmonic, but that's what it is. So that are the AC emulators. We have 4 of 90 kilowatts, so 360 kilowatts in total. We also have a DC emulator. We need that to create a DC source. At one hand, to provide the power to charge a car, or dissipate the power that is given by a charging station. Like also Tim told us in their presentation, the voltage of charging can have an influence on the power quality. And with this system, we can create all kinds of voltages. So it can from 100 volt up to 1000 volts. So we can see what is the power quality of certain chargers at certain voltage levels, and we're not dependent on a battery. The last thing is the charging discovery system. Yeah, this is basically the brains of the system. Like Wolfgang told you, we can connect the DC emulators to it, we can connect the AC emulators to it, cars, charging stations, we can connect it to our back office. Yeah, so it's taking care of the control and the communication part. Yeah, now I'm going to explain the test setup we have right here. The first test branch we have is for EVSE testing. So over here we connect the AC emulators to the grid. The AC emulators are making a clean grid that we can connect to the charger. Then the charger is connected to the charge discovery system, and the charge discovery system is connected to the DC emulators, which are connected to the grid again. So we have, yeah, in the loop, so we don't only use the energy that is dissipated. The second test we have is for EV testing. Instead of putting a charger to this charge discovery system, we put a vehicle to it, and then we can, yeah, test that vehicle on smart charging, vehicle to grid, 15L8-20. And the last one is man-in-the-middle testing. So we can place the CDS between the charger and the EV, so we find some charging problems. And I think now it's demo time.
Yeah.
So the first demo setup is this. We're going to test key site against key site to show you that it's able to work with 15L8-20. Then we're going to use a real charger. Going to use the MB box, and afterwards we go test the test system on full power. So we use a bigger charger.
Also, the reason is that it's tough to find a vehicle that supports ISO 15118-20 as a specimen. But we can start the demo with this one.
Yeah. So I think you can take over, Sven.
In the upper part here, you can see that we are operating as an EV. As Wolfgang already mentioned, it's not that easy to find a car already today which have that implemented. This is why we try to emulate it today. You can also see kind of measurement for the proximity, for the control pilot here, and also the power part. On the left side here, you see then the plotting over time about all the measurement data. And on the right side, you see a list of parameters you can modify. This is based on setups that you can, let's say, emulate different kinds of EV with different voltage level, different amperature, different maximum power. Also, in terms of timing, you can modify your timing behavior for all the kind of messages which are sent and received. And this is what you can see up here in the called progress bar, which is indicating which step you are in during the protocol exchange. So a lot of messages are going back and forth between the electric vehicle and the charging station, doing a ramp up of the charging station to build up a session. Then you have authorization, you have charge parameter discovery, so what are my maximum and boundaries, in what kind of boundaries we can operate. Then you have a cable check for safety reasons. We have seen that already in various kind of presentations up front. And last but not least, we end up in the charging loop, which is already at the very end over here. Yeah, and then you only have a welding detection and session stop. This is just closing down then the charging process. So what I try now to start is the charging process with the let me unlock it first.
Laptop is locked. Thank you.
Yeah, so you have maybe seen in the upper part here, let me check the mouse, that the progress was pretty fast, so there's a lot of messages going back and forth. And right now we are already in the charging process, but you can see here over time there was a ramp up of the current and first of the voltage to check the cable, then going down and then ramp up the current for the charging process. Right now we are in the charging mode. We also have an overview on the lower part here about the session data, which we see what is the actual data sent back and forth in the messages. And you can also see here the logging information, how many loops are already done for the communication. And if we now go in the charging environment, which is back here, if we go from charging to discharging, you will also see that we go here in the negative part. So we are now powering energy back to the grid, and you see also that on the blue part here that we have charged with not much, but we drop down then to a discharging of about 10 amps here. This is, let's say, the normal setup that we can showcase that 1511.8-20 is working with DC bidirectional. Okay, so next setup will be that we stop the process. We have also here two options. You can do it in your car, press the stop button, or also at the charger to press the stop button. I will just do it here from the car. And now we would switch over to our next demo setup. So that was just test system against test system, where we use the Ambibox, which are also here today. And we can plug out the test system, plug in the Ambibox system.
Go.
And yeah, we will try the same again. So same parameter set, just another system under test. And you can also see that we go to the specific parts of the process. But now you can also see if something unexpected happened, that it directly stays in red, and you see, okay, something went wrong. Yeah, so you need to restart? Okay. So what we have seen is just that the charging station stopped, and we can then see, okay, it went from the state B here to state EF. And we will start one more time. So there's no signal from the charger coming.
We need to plug it in and out.
Maybe try.
It's always the same with demos. But be patient.
It's live.
It will work.
So there's no duty cycle coming from. Okay. Yeah, then maybe we skip this first for now. Maybe after the session, if we have another break or coffee session.
I think during the drinks, we'll make sure the demo is working, and you can check the.
Yeah, we can then
the
start
demo
over
with the
again.
Ambibox, which is doing bidirectional charging. Then I think we go to the last.
Okay.
Last setup. Can you change the parameters? The last setup is the high power testing setup. We connected the ABB charger over there to the CDS. First the EC emulators, and then we connected to the device under test. And that's also the point where we measure the power quality. So we measure on voltage and current, and we do that on really high bandwidth. We do it with 1 megasample per second. Then we connect the charging station in the CDS, and the CDS is dissipating the power to the DC emulators. Sven is right now doing some other parameters, so we can up to high powers. In the meantime, I will connect it. maybe we can switch back to the testing screen so you can see what Sven is doing. He is restarting the test. Runtime, yes. Yes, that one. Cool. And then we need to fill in some parameters that we are making sure we have the right power. This can take a while. Maybe I can tell you some interesting facts about the building. We're here in an old, Axel Nobel building. We used to make glass fibers over here. So I don't have more interesting facts right now. So we wait. Okay. So this can take a minute.
Yeah, so maybe you can also see here that a lot of protocols you can choose, but I think we will start with the old one,
yeah.
with DIN.
Okay, then yes.
Then we also want to start with the power flow. We want to...
Now we're setting up the car we want to emulate. Oh, something.
So we go with 950 volts.
Indeed. So we set the maximum voltage of the car to 950 volts. And then we say the maximum, it's that one. The maximum power is 330 kilowatts. We fill that in, that's the amps. So yeah, the we state what the initial battery voltage is and what the battery voltage is that we want to climb to. So we start with 900, we want to go to 920 volts. And we need to, yes, 920. Yes, and we need to disable those buttons. Yes, active power flow is on. So I think we can start the test. We can shoot this one. Charging loop. Yeah, there we go. Sure, maybe we can zoom in on this number. Is that possible? Yeah, I think that is possible. Yeah, as you can see, the active power. Oh, it's a bit. Go back. Yeah, the active power flow right now is 330 kilowatts. That is going from the grid emulators to the charging stations and back to the DC emulators again. I think that was the last demo. Yeah. Maybe some time for questions?
Yeah, sure.
So we, shall we stop it? Yeah, it's a bit noisy.
Okay, thank you for this great demonstration. And please join us on stage. Yes. I think if you're a tester, you're very familiar with this, and the great value for ELAT is that this keysight system allows us to see what's happening, and if it doesn't work, and this is what we experience, oftentimes it doesn't work, but then if you don't have a test system with this level of detail, you don't know where to look or where to go debugging, and this is the great value, that even though it doesn't work, you can at least get some more information on what to do or where to go. The charging station that we had with the -20 was something that we were donated a couple of weeks ago, or at least a month ago, so it's very new, and we're really happy that we have that to test with and learn more.
That is changed. It's just arrived today.
Oh, today actually. Oh, I didn't know that. So this Ambi box, it just arrived today. So this sort of also shows how fast things are developing and how new everything is. And with this Keysight system, at least we can have a look and drill down in the interaction between the charger and the vehicle, or the other way around. So questions for Keysight, for Robert from ELAT. Do you have any questions about the system? Do you want one? Do you want to buy one? They're in high demand, so we know. So it's of course a big system. It's sort of modular. So at ELAT we have this 360 kilowatt setup, but of course you can buy a lot of different combinations. So it's very flexible. No questions, Thijs? Would you like to ask a question, as you have now the first a couple of months experience with this system? Any feedback for Keysight?
Well, it's working great, but the thing is we're already looking for expansion, because, well, 360 kilowatts, we're now phasing up to megawatts. So, well, Mel, you were saying, that might be interesting, because we were saying, well, you're building a new system, well, you're building up new systems that are capable for megawatt charging, but the existing systems, will they be upgradable too for megawatt charging?
Correct. We have, of course, a huge install base of the system, and the customers that want also to go into the right direction, megawatt charging. As I showed during my presentation, standardization is still ongoing, but we want to enable the level of testing that is possible today as early as possible for the customers as well. And therefore we cooperate here also with the customers and say this is possible. This needs maybe a little bit of time because standardization is ongoing, but we have high hopes that at least the end of this year we have a solid technical alignment at least reached. Maybe not every standard is published, but the technical freeze could be reached, and then we could serve a complete test solution.
Thank you.
One question that I have is, of course, we use the system for multiple types of tests. So we can do the power quality testing, the bidirectional charging testing, but also the protocol testing. And you mentioned all the different standards and standards evolution that are there. We know that there is ongoing work in the US, also on ISO 15118 Lite, and even of that they have two different sub-flavors. And it is crucial for the future to follow a standard, because otherwise you face the interoperability issues that Beat showed us in his presentation already with CCS and DIN. And of course with Dash 20 it's becoming more and more complicated. One thing that from our view may help is the sooner you have test cases available for the industry and test systems available for the industry, the sooner you'll find deep bugs and the sooner you'll get better implementations out there. Which brings us to the time between the publication of a standard and the becoming available of a test system and the development of the test cases in between. So do you have any views? I have a personal opinion based on the Open Charge Alliance, but do you have a personal view from the Keysight perspective? What would we need to do as an industry to speed up the development of test cases and subsequently development of the systems?
Yes, of course. That are all humans that work into these groups. That is important. But yeah, to focus, of course, the relevant aspects and to fix the relevant aspects with priority. I think the colleagues already tried to do that, but of course there are multiple opinions available, and therefore, yeah, unfortunately, standardization needs its time, but it's usually also well invested time because then the standard is way more mature when it comes to public. I know that it's not fast enough for the industry, it's also not fast enough for us, to be honest as well here. However, what we see is then a lot of pilot projects where we also receive requests, can we not have a test system for these kind of pilot projects? However, we also say that, yeah, well, it's important that everybody is aligned and that we focus on a joint and harmonized standard and not have too many individual fragmented, let's say, proprietary solutions also in the market.
If I can add to that, so now I will share my personal opinion, is what is really important is if you want to write a test case and if you want to build a test system, it's a lot of work, which needs to be done by people that need to eat, so they need to be paid. At certain standardization organizations, the work is all voluntarily. So also the writing of test cases is asked of the industry that are most of the time commercial companies, so they have to make money, and also they have a lot on their plate. So this makes the development of test cases slow. It's sort of like voluntary work. So what my personal opinion is developing test cases as part of a standard is so important. If you could fund that, so if you can pay technical editors, people, doesn't matter, just pay to do the legwork, come together and fund that, and that will benefit everybody. So the reference we of course have is with the Open Charge Alliance and OCPP, and this is what we do at the Open Charge Alliance. So members join the OCA, they pay a little bit of participation money, and with that money we pay technical editors who actually write all the test cases. And then of course provide them for review and for feedback. And in our industry, which is charging stations and back offices, companies do find the time to review test cases, but don't have the time or the funding to do the legwork. So that would be my suggestion. I don't know who to tell this, either Charin or ISO or the European Commission, I don't know whom, but that would be my suggestion. Just set aside some money to fund a couple of smart people to do the legwork, develop the test cases, and then everybody in the industry will be allowed to go much faster. That would be my advice. I'm not sure if you agree to that.
Yeah, I think it's more complicated than that. Or that idea is basically not 100% new, I would say as well. So it's in different standards, international, national, locally. So that's a little bit more complicated. Overall, I do agree that there could acceleration be reached by dedicated personnel. However, I think it's basically following a certain process that is well established. So a group of people is assigned, there is a lead assigned, there is a timetable. However, and unfortunately also based on my experience, the target times are not that well maintained. But it's a democratic process. It's important that everybody gets a voice who has a stake there. And the more and more people are coming, and that's also what we expect, for example, in Charin. It was a small group of people, but then the community grew and grew and grew, and more opinions came in. And of course, this is slowing down the process, but also it improves, at the end of the day, the quality of the process. My personal opinion.
Okay, great. Any questions before we sort of close the session for the official part? And then, of course, behind the chargers there are some drinks and snacks awaiting for you to discuss and ask more questions if you like, and meet. So final check. Any final questions? No? Okay, then I'd like to have a final round of applause for Robert and Wolfgang.
And Sven, of course.
And Sven, of course. Sven, of course.
And the people
Not to
from
forget Sven.
Ambibox.
Thank you for your time. Thank you for listening in. We are here every day of the week. That's the weekend. So if you want to come by a later date, talk some more, test some more, you're more than welcome. And thank you for your coming and join us for drinks.